Okay, so if we consider the region in the xy plane bounded by the curves y equals root of x, the y-axis, and y equals 2, and we revolve this region about the y-axis, we generate the given solid of revolution, which is a very nice little solid. And the question we want to ask now is, what is the volume of this solid of revolution? Now, if you remember, we solved this problem in the previous video using a set of horizontal rectangles, and this was our solution. Our horizontal rectangles generated disks. Disks were little cross sections of the full solid. We found the volume of any given little cross section positioned along the y-axis, pi y to the 4 dy, and by summing the volume of every little cross section of every little disk as y ranges from 0 to 2, we obtain the total volume of our solid of 32 over 5 pi units cubed. We want to solve now the same problem, but instead of using a set of horizontal rectangles, we want to use a set of vertical rectangles. And we'll see how different the solution will be in this case. But hopefully, if we're not making any kind of mistake, we should arrive at 32 over 5 pi, as we are finding the volume of the exact same solid using a different method. Okay, let's see. So we take a small infinitesimal vertical rectangle. It is positioned along the x-axis. The width of the rectangle is a small change along the x-axis. Of course, we denote an infinitesimal change in x by dx. Now, if you notice, the difference from a vertical to a horizontal rectangle is a vertical rectangle now is parallel to the axis of revolution. And if you revolve a parallel rectangle to the axis, and again, because the width of the rectangle is dx, an infinitesimal change in x, or if you prefer, a change in x shrinking to 0, you can think of this rectangle as a very thin piece of string. And as you revolve this rectangle that is parallel to the axis of revolution, this will generate a cylindrical shell, which you can think again as an aluminum can where the top and bottom is missing. So let me produce a sketch here. So we have our cylindrical shell, and as always, the center of the cylindrical shell is the axis of revolution. So if you remember, to find the volume of such a cylindrical shell, we need three things. We need the height of the shell, which is clearly the height of the rectangle. We need the radius of the shell. We'll denote this by r. And we need the thickness of the shell, but we know that the thickness of the shell is the width of the rectangle, that is of course dx. Okay. So let's find these two quantities. First, so as I've just said, the height of the shell is the height or the length of the rectangle. That is a line segment along the y-axis, so we need the larger y value minus the smaller y value. So let me extend this segment over here. Now here at the larger y value, y is always equal to 2. So 2 minus the y value here being the smaller y value. As we have a dx, everything that we compute must be a function of x. But here we are on the curve y equals root of x. So the y value here is root of x. So the larger y value is 2. The smaller y value is root of x. Therefore, the height of the rectangle is 2 minus root of x. There you go. Now we're missing the radius of the rectangle, not the rectangle, sorry, but the cylindrical shell. We can see that r is the distance from the center of the shell to the rectangle, but the center of the shell corresponds to the axis of revolution. So if we go back to the picture in the xy plane, we must find the length of the segment connecting the axis of revolution, in our case the y-axis, to the rectangle. Axis of revolution to the rectangle. So axis is here, rectangle is here. This is now a horizontal line segment. So we'll need the x values. So let's drop those two down. So this is our radius. The distance between the axis of revolution and the rectangle. As I've just said, this is a segment along the x-axis, so we need the two larger x values. As we have a generic vertical rectangle, it is positioned along the x-axis. Its position is x, x being the larger x value, minus the smaller x value, but at the y-axis, x equals 0. So the radius of our cylindrical shell is simply given by x. And now we can find the volume of this cylindrical shell. Now this is of course slightly more complicated than a simple disk. But if you remember, there was a very simple but very nifty little trick to simplify this solid. If you think of this again as being an aluminum can with no top and no bottom, and having a good pair of scissors, you can cut through one side of the can, and then you can press on it and flatten it out on the surface, and then the can becomes a rectangle. So you need the area of the rectangle. It will be the height times the length, but the length will be the circumference. The circumference, of course, is 2 pi r. Times the height gives you the area of the corresponding rectangle, times the thickness, dx, gives you the volume of the cylindrical shell. Again, if you need a reminder, you can watch the video that introduces you to this formula. And now we have found the radius and the height, so we can substitute in. This will be 2 pi. The radius is quite simply x, so 2 pi x. The height is 2 minus root of x. And of course the thickness dx. So now we have the volume of a small cylindrical shell. The question is, how do we, from knowing the volume of such a cylindrical shell, obtain the volume of the total solid of revolution? Well, let's see, right? Here's the entire region in the xy plane, and as you revolve this entire region about the y-axis, the axis of revolution, you generate the complete solid. But now we take not the full region, but a little cross-section of it, a little vertical rectangle. So let's try and see what happens. Now if you revolve not the full region about the axis of revolution, but instead the small vertical rectangle, it will generate a cylindrical shell, it is right here, within the full solid. So let me try and reproduce this. And so you can see, by taking a little slice of your entire region and not revolving the full region about the axis of revolution, but simply a little portion of it, the little rectangle, you generate a nice little cylindrical shell within the complete solid. And now what we have is that we know not the volume of the full solid, but we know the volume of this nice little cylindrical shell within the full solid, and here it is. So of course you ask, how can we, from knowing the volume of this little portion of the complete solid, then obtain the total volume of the solid? Well, of course, if you think of taking different rectangles over the region, you will generate every little cylindrical shell within the solid, and as you add the volume of every possible cylindrical shell that lies within the full solid, you will obtain the total volume of the solid. And of course, the action of summing is the action of integrating. So the total volume of the solid of revolution is obtained by summing the volume of all of the little cylindrical shells that lie within it. Summing, as I've just said, is integrating. Well, what is the volume of this shell? It's right here, so 2 pi x times 2 minus root of x. I will not write root of x, but x to the 1/2, thinking of integrating using the power rule, times dx. Okay, so as I've just said, we have now a little cylindrical shell that lies within the full solid of revolution. The volume of this shell is 2 pi x, 2 minus x to the 1/2 dx. And to find the total volume of our solid, we sum the volume of every little cylindrical shell that lies within it. Now, where do they begin? Where do they end? Well, our shells are generated by the vertical rectangles across of our region. And the rectangles, again, along the x-axis will begin when x equals 0, and they will go all the way up to x equals 4. So you have to sum the volume of the cylindrical shells as x ranges from 0 to 4. And by adding the volume of every little cylindrical shell within the full solid, we obtain, of course, the total volume. And if we didn't screw up anything, we should arrive at the same answer as we did previously using a disk. And the answer was, if you recall, 32 over 5 times pi. Well, let's see. We can't integrate just yet as we have a product between two functions of x, but if we multiply through, the product goes away, and then we can use the power rule. 2 pi is a constant multiple. We can factor this out. This will simplify our integration. And if you multiply, you'll get 2x minus x times x to the 1/2. Well, 1 plus 1/2 is 3/2, so x to the 3/2. And now we can find the antiderivative using the simple power rule. Integrate 2x, you obtain x squared, minus, add to 3/2, 1, gives you 5/2. And you must, of course, divide by 5/2, but if you divide by 5/2, you multiply by the reciprocal, which is 2 over 5. This is the antiderivative of the function, and we must evaluate by the fundamental theorem of calculus from 0 to 4. And now we can just plug it in. We have 2 pi, and we evaluate at 4, well, 4 squared is 16, minus 2 over 5. But here, let me evaluate first 4 to the 5 over 2. Take the square root first. Square root of 4 is 2. 2 to the 5 is 32. 32 times 2 is, of course, 64. Well, to simplify, we must put 16 over 5. Multiply by 5 over 5. 5 times 16, of course, is 50 plus 30 gives you 80. So you have 2 pi. Oh, and I skipped ahead here. Of course, this is simply the value of the antiderivative at x equals 4 minus the antiderivative at 0. But if you plug in x equals 0, you get nothing. So it really is just the antiderivative at the upper bound, as the lower bound gives you nothing. So if we, as we've said before, 5 times 16 is 80. Eighty minus 64 is 16. And so we have here 16 over 5. And if you multiply 2 by 16 over 5, you get 2 times 16, 32 over 5 times pi. And good news, this is the exact same answer we obtained in our previous video where we used a disk instead of a cylindrical shell. But in both cases, we find that the volume of our complete stellar revolution is exactly 32 over 5 pi units cubed. And you can appreciate how elegant in both cases the solutions are, because we are really finding the answer to a very non-trivial question, right? The solid we found the volume of is highly non-trivial, and yet the solution was very elegant. So there you go. Now of course you can notice that using the disk was a little simpler in this case than using a cylindrical shell, but these two examples were twofold. The first reason was that to solve a problem in two different methods and arriving at the solution gives more support to both solutions, and in some cases it will be the opposite. In this case it was simpler with a disk than a shell, and other problems a shell will be better than a disk. So keep this in mind that you always have two options: vertical rectangles or horizontal rectangles. And that's it. Of course I have to go up and include this because I have to say I'm very proud of this picture. You have to admit it looks pretty good.